This assignment is related to astrophysics and cosmology questions. Question 11, in the early 20th century, Edwin Hubble carried out research on objects known as the extragalactic nebulae, and the light spectra emitted from these are found to be shifted from a wavelength measured from a corresponding source in the lab. And now we recognize that like these nebulas are galaxies, and the wavelength shifted are evidence of expanding universe. Hubble used standard candle to determine the distance. How a standard candle is used to determine the distance? You normally, when we apply the concept of standard candle, we say that this star or this object is having a known luminosity. So we know the luminosity of the object. So object which having a known luminosity, like standard candles have known has a known luminosity, and what we do, radiation flux or a brightness of a candle be measured on the earth, and then we use the formula, like we have the formula that the flux is equals to luminosity divided by 4 pi d square. So what we do, like example, this galaxy or a star we focus on, we know its flux. That is a rule, like standard candle, and we are observing on the earth, so we measure how much flux we receive from it. Like flux means how many radiations we receive on unit area. It's emitting out, but how many radiations we receive on a unit area, that is called a flux. So we measure the flux on the earth. So we measure the flux, and what is d? D is the distance between the object. So d is the distance between the object, the source, the standard candle, and the observer. So we can work out this d. So if we need d, it will be d square is equals to luminosity divided by 4 pi into flux, or we take a square root to get the distance. So how to write such answers is, in this answer, what you will mention, like how standard candle can be used to determine the distance. So first point, which score the mark, you will mention a stellar object with a known luminosity. So the standard candle is object of known luminosity. So we know the luminosity of an object, and after having a known luminosity, the brightness or the flux of a candle is measured at Earth. And then we use inverse squared law to calculate a distance, or you can just mention, we'll use a relation F is equals to luminosity divided by 4 pi d square. So L and D are identified, we know, so we can work out the distance. In part, to suggest why some standard candle can only be used to determine distance relative to close galaxies. So the idea is that because for more distant galaxies, like when the galaxies are too far from us, it will be difficult to measure the flux. The flux or intensity will be too small. So we don't receive to, if the objects, like the object on which we focus, it's too far from us, so we won't be able to receive a very small amount of a light we'll receive from that. It is emitting out light, but the flux which we have, that will be very small amount as compared to objects which are closer to us. So when we are measuring their flux, it will be easy to measure the flux or for the objects which are closer to us. So the idea suggests why some standard candle can only be used to determine distance to relative close galaxies, because if the galaxies are far, the flux will be very small, or the brightness will be too low, or we may not receive all the light or a very small quantity of a light. That's why it will be difficult to determine the actual distance. Then once the distance of a nebula has determined, Hubble used the values of a wavelength shift to conclude that there was roughly linear relation between the velocities and the distance. Describe how Hubble was able to determine the velocity and explain how his conclusion provide evidence for expanding universe. So what actually, like how we can determine, first we'll determine the Doppler shift. Using a Doppler shift, we can determine what is the Doppler shift. The Doppler shift is change in wavelength over original wavelength or change in frequency over original frequency. So using a change, like observing what frequency we receive from the stellar object, we compare that with what we receive on the what we get in the lab, and we compare how much the wavelength or frequency changes. So first, Doppler shift, we're using a Doppler shift, calculating a Doppler shift, and from Doppler shift we can find the speed of the galaxy, that z is equals to v by c. So this multiplied will get the speed of the galaxy. And how we identify whether it is moving away or towards. So if the galaxies are giving a red shift, if the wavelength is increasing, these galaxies are moving away from us. If the and after working out the distance, like after working out the speed, first using a Doppler shift, work out the speed of the galaxy, and then we know the speed of the galaxy, the resistance speed or a velocity, and the distance of a galaxy. There's a linear relation as the distance of the far galaxies which are further or far from us are moving at a higher speed as compared to galaxies which are closer. So using the speed of the galaxy, we can determine its distance from us. And using a Doppler, like example, the galaxies which are further moving, and for therefore the galaxies which are moving away from, most of the galaxies are giving a red shift, or they're moving away from us. That's why, so all the galaxies are moving away from each other. So it must be universe expanding. So first thing, using a Doppler formula, or we will work out the velocity of the galaxy. And how we know it is moving towards or away? Because it is, if the red shift is there, like the wavelength is increasing, it means that it is moving away. So using a Doppler shift, we work out the speed of a galaxy and conclude that it is moving away. And then we check these galaxies, that as the distance, the further the galaxy, they are moving faster. So higher speed means they are far from us. If they are far from us and the distance is increasing, it shows that the universe is expanding. In question 12, curve ABC shows the radiation spectra of a star with different surface temperature. As you can see, as the surface temperature increases, the peak wavelength decreases and shifted more towards the, this is a intensity is there, and shorter wavelength means higher frequency or more power, because what is the relation between wavelength and temperature of a star? It is inverse. And according to Wien's, lambda max into T is equals to 2.89 into 10 to the power minus 3. So if the wavelength decrease, the temperature of a star increase. So you can see the peak wavelength for ABC. A is having a shorter wavelength. So it means star A is having the highest temperature. The curve B represents the radiation from a sun. State evidence from a graph suggests that this might be so. Like how this is an evidence, like this graph is representing a sun. So the sun, we are able to see the sun, and this is a visible range. Like from 400 nanometer, which is violet, and the 700 nanometer, that is red. So sun, we can see the sun, and sun is emitting out, ultraviolet is there, but we are able to see the sun. So means it is giving the light in a visible range. So that's why it is an evidence like B is representing a graph of the sun. What if the peak wavelength was above 700 or below 400? Then we won't be able to see that, or very small amount will be there in a visible range. State with a reason which curve represent the star with a greater surface temperature, that is A, because the shorter wavelength, so higher temperature as they're inversely proportional. Use the graph to explain how the radiation from star identify in to differ from a radiation from a sun. So how these two radiations are different? So the curve peaks at a smaller wavelength, like as you can see, the star emits more blue or ultraviolet radiation, where sun is giving most within the visible region. And area under the curve is so large, so star has a greater power output, whereas the peak of a curve is a higher, so the star has a greater power output. So how they're different, we have to just check how they're different. A is having like this is in a violet region, or peak is there ultraviolet, so it will give mostly ultraviolet, blue or violet or ultraviolet. But B, which is a sun, mostly it will give visible. And it's having a high power, like it means it's having a high temperature or high power output, or it will be much brighter if they have the same distance from the Earth. Stars other than the sun are too far away from the Earth us to make direct measurement. Explain how we can deduce that some of the giant stars and some are dwarf stars. Like how we can identify the size of the star. So what we actually do, we determine the luminosity and the temperature. Like first, they say star other than the sun are too far from us to make the direct measurement of a diameter. Like we cannot measure the size of the star. How we can identify that this is a giant star and this one is a dwarf star? The size of star is different. So what we actually do, we record the wavelength which we receive from these stars. From the wavelength, we have the formula lambda into t is equals to 2.89 into 10 to the power minus 3. So from the wavelength, we'll determine the temperature of the star. So it will be 2.89 into 10 to the power minus 3 divided by wavelength. We get temperature of stars. After measuring the temperature of the star, we have and we measure the luminosity, like the power of the star as well. Like we'll have a graph for luminosity and power. And if you know their so we will work out the luminosity, and we have the formula according to Stephen Boltzmann. Luminosity is equals to 4 pi r square sigma t raised to power 4. So if we have the temperature, we have luminosity. So where r is the radius of the star. So we can work out the radius of a star. So we need luminosity and the temperature. Using a luminosity and temperature, we use a Stephen Boltzmann law. And we can also, there's also another way, like we can have a Hertzsprung and Russell diagram for a graph for luminosity and temperature of the star, like to 24,000, then 12,000, then 6,000. And this will be the main sequence star. So we can identify the type of star, like here we'll have white dwarfs are there, here we'll have a giants. This is the main sequence. So we can also plot a graph between luminosity and temperature and work out which position this star lies. So we can also state the type of a star, whether it's a giant star or a dwarf. For the star which are relatively closer to the Earth, describe how a parallax measurement can be used to determine their distances. For parallax measurement, better you should draw as well, because if you score even full mark, you will obtain if you draw a suitably annotated diagram. Like if your diagram is suitable, correct, you will score the marks. So here, this is a sun, and we have Earth, and we have fixed distant stars. And we consider like this is a axis, the origin, and this is a star where we are focusing. So this is star we wanted. So what we do, we measure this, observe this star, and this angle we measure, we call that example theta 1. Then after a 6-month duration, we measure, and this is like comparative distance between we measure its relative to the origin, like relative to the distant star after 6 months. We measure the distance of this star again, angle, the change in angle, and that is we call theta 2. After a 6-month duration, we observe that. And the distance between Earth and the star, Earth and the Sun is known, which is 1 astronomical unit. So we using a trigonometric ratio, we can determine this distance d. So if your diagram is fully annotated, you can use a trigonometry is used to calculate d. So you can draw this diagram and you will score all the marks. But if you want to write, so I prefer that you draw as well as write. In case your explanation is not complete, you will score the mark. So what we do, the star is viewed from two position at a 6-month interval. So we observe the star. So with a 6-month interval, we observe the star. So like the star is viewed from opposite end of a diameter of Earth orbit. Then change in angular position of a star against the background or a distant star is measured. Then what we do, we use a trigonometry is used to calculate the distance to the star, and a diameter or a radius of Earth orbit is known. So what we can do, we can use a trigonometry. So a trigonometry we use to measure the distance of that, but trigonometric parallax is only valid for nearby star. Why we cannot apply it for the star which are too far from us? Because if the stars are too far from us, when we observe them for a duration or a period of a 6 months, the change in like if any star is closer to us, the change in angle will be considerable. Like percentage uncertainty or uncertainty will be reduced. But if it's too far from us, the change in the angle will be very small if we view. As a result, the uncertainty will be higher. Percentage uncertainty will be higher. Is it clear? The trigonometric parallax. So trigonometric parallax, standard candle, and then the Doppler shift, they all can be used to determine the distance of the stars.